Hey guys, it's Mr. Riz, and we're going to start Chapter 1, Section 1, and limits on their properties. So this is going to be a preview of calculus, and we're going to kind of go through this pretty quickly. The first two sections we don't spend too much time on in Chapter 1. Alright, so a preview of calculus. What we want to do is make sure you guys understand what is calculus and how it compares to pre-calculus, which you guys took last year. And there's going to be two big things that we're going to do. We're going to understand that the tangent line problem basically is the basics to calculus. It's a huge thing we'll do. And also understand the area problem. It's another big thing. So this is first thing we'll talk about, like first semester. This is second semester stuff we'll get really into, but we can still talk about it today. Okay, first, what is calculus? Well, calculus is the math of change. For instance, calculus is the mathematics of velocities, acceleration, tangent lines, slopes, areas, volumes, and arc lengths, centroid, curvature, and a variety of other concepts that have been enabled scientists and engineers and economists to model real-life situations. Although pre-calculus mathematics also deals with velocities, accelerations, tangent lines, slopes, and so on, there's a fundamental difference between pre-calculus and calculus. Pre-calculus is more static, whereas calculus is more dynamic. Here's some examples. If we have an object traveling at a constant, and that's the big word, constant, whoa, wrong button, constant velocity, it can be analyzed with pre-calculus. To analyze a velocity with an accelerating, so if we have a changing object, we need calculus. We can find the slope of a line with pre-calculus. Now we're going to be able to find the slope of a curve. Also, the curvature of the circle is constant, but if we want to analyze a general curve, we're going to need calculus. And so you guys can see anything that is constant, like a rectangle has constant sides, we're going to be able to calculus to do things more general with curves. So here's the big thing. Calculus introduces the limit process to pre-calculus. So if we have like all the pre-calculus math that we did last year, and we add this new concept, which is Chapter 1, limits, what we're going to get is basically what calculus is all about. So here's a bunch of things that we're going to do. Actually, these are going to be 4 things that we're going to hit heavy in the first semester. These will be dealing with things called derivatives. These are some things that we might get into. So the curvature of a curve. Here's a big thing, the maximum height of a curve. We'll be able to find those. And then some other things we might get into. Later on in the year, we're going to talk about integrals. And so you can see integrals, we can find areas underneath the curve, and we can determine work done by variable forces. Other things we might get into, but I don't know if we'll be able to cover it within the whole year. And here's something, probably the last thing we do in the year is finding the surface area of a solid revolution. It's pretty interesting stuff, and it's good. And also, we'll probably get to this part too, the sum of an infinite series. Alright, one of the biggest problems that we will have throughout the year is the tangent line problem, and we'll go throughout figuring this several different ways. And we're going to start right at the basics where people first started trying to think of this problem, how they figured it out. Now I'm going to be extremely brief with this explanation because later on in the year we'll learn different ways that are a little bit more efficient than what we're going to do. So here's the notion, is fundamental to study of calculus. The following describes brief of 2 classic problems in calculus, the tangent line problem and the area problem. And this should give you an idea of the way that limits are used in calculus. Alright, so here's the tangent line problem. Say we wanted to find the slope of a tangent line. If you don't know, a tangent line is a straight line, constant line, that touches the point of the graph at one point and doesn't cross the graph anywhere else. Alright, so we would need to know the slope of this line. Well, what we could do is create a secant line. And what a secant line does is connects 2 points of the graph. Now as we get closer and closer, so if we pick a point here and get closer and closer to that the slope of the tangent line will get closer and closer to. So as I pick a part closer and closer, so if I can go back, oh no, I really can't delete anything. Yeah, I'll move it out of the way. Oh, no, I drew right on top of it. If you guys can see, what we have here is the change in x. And so here's our one point that we start with, c and f of c. So basically our x and y values. And when our change in x gets closer and closer to 0, we're going to have a slope that gets closer and closer to our tangent line. So what we could do is figure out, since we have the point c and f of c, or basically this is our x and, ooh, that's the worst x ever written, and y. We could have another point, which is our x plus delta x, and our y with respect to that. And we can find the slope of the secant. And so this is a huge formula right here that we're going to use a lot later in the year. Basically, because we have our x1, y1, and our x2, y2. And so we plug that into the slope formula, subtract the y's, subtract the x's, where do you get that function? So that you can kind of see what I redrew here. As the limit, what we're going to be talking about, limits here, is we get closer and closer and closer to 0, that limit is going to get closer and closer to 0. Now we can't plug in 0 because that would be undefined, or we'd get the exact same point. There would be no slope. But as we get closer and closer and closer, as that limit approaches 0, we're going to figure out the slope of the tangent line. So what we could do is start picking values that are closer, and we probably want to pick ones that are on the other side as well. So we approach from the left and going to the right. Alright, now the area problem is a little bit different. If we're trying to find the area underneath the curved graph, there's no way to do it unless we can just find the area of rectangles, because those are just length times width. So what we can do, we can take this shape and break it up into several rectangles. Now obviously these rectangles aren't going to be exactly the same area as the curve, but it's going to get close. Now what we can see is that each rectangle, the more rectangles we have, the closer to the area we're going to get. Now if we were to find the area of each rectangle, we'd have to know the change in x, and we'd have to plug in the f of x function. And you have to keep in mind we're going to use only those 3 points, because here's like f of 0, f of 1, f of 2, f of 3. Even though we have 4 blocks, we have to remember we go 0, 1, 2, 3. And same thing here, we count all those. Now it's a limit because what we're going to do is increase the limit of the number of rectangles to infinity. And so this is going to be some things we do. I know I went really briefly through this, but you guys should be able to kind of figure out what we're going to do in this chapter. There is the 1.1 and the 1.2 homework quiz. And so if you're having trouble with that, let me know, because those won't be due till the end of section 1.2. Alright, good luck.